So we're going to talk about building Kubernetes distro the easy way. First of all, a little bit about myself. I work for Puppet. I'm a principal software engineer, possibly going to become a product owner in the coming weeks. I work on all the cloud native space. I have 3 teams now that go underneath me, and like they're all over the world, so it's really distributed. And
I'm Dave. That's me. I work in one of Scott's teams, also at Puppet, primarily working on anything container and cloud related, and nothing to do with Puppet Enterprise. So don't ask me about anything related to Puppet Enterprise while I'm here, because I can't answer your question.
Yeah, we don't do a lot of Puppet in Puppet, which is kind of strange, but it's good. In this talk, what we'll cover is building a Kubernetes OS. And why would you want to do that? The use case to do that. Then building the OS is actually the easy bit. What about the day 2 concerns? Like what happens when you want to do upgrades? Security, and then we'll tie it all together and like how we do it. So why do we want to do this? First of all, I'll give you some use case. So we have an application that's been released now called Puppet Pipelines for Containers, and it's a name that doesn't really tell what it does well. It's actually a lifecycle management tool for Kubernetes, and it looks at the application layer only. But underneath that, we needed some way to provision Kubernetes clusters. At the moment, we can do that with GKE, straight into GKE. But we had customer requests saying that they wanted to either use an on-prem with VMware. They wanted to have it in their own space in the cloud, in a public cloud. So they wanted to control the image. They wanted to do everything themselves. They didn't want it to be a hosted service. So we had to come up with a solution. The first thing we looked at, and of course they asked us to do, was build a Puppet module for Kubernetes, which we did. It works, but when you're competing against the timing of something like GKE takes roughly about 4.5 minutes, 5 minutes for a cluster to come up, maybe. The Puppet module, once you install Puppet and stuff, was like 13 minutes, so that was out the door. And then we started to look at a lower level. I'll let you talk a little bit about this.
Yeah, so just out of interest, has anyone actually used the Puppet Labs Kubernetes module?
Yes.
Good. That's what we thought.
There is a whole heap of people using it, because there's a whole heap of open issues on GitHub and
cool.
stuff like
that. So I guess...
we need to talk about this a bit more. So first of all, we thought we'll build an OS. What's wrong with a traditional OS? So if you saw my talk at Container Camp last year, I spoke about it's in a container, it's secure, right? This is kind of the next iteration of that talk. When you talk about distributing an OS to a customer site, you've got to take into all the operational concerns that they will want. So what about things like patching? There's vulnerabilities that's been released. All these sort of things we had to think about. And what we found when we were doing a project working on shipping PE to Azure on Debian, and I love Debian, don't get me wrong. That's what I'm running. That when we were using Packer, it took so long to build, and then we had to run security concerns and locking down a whole heap of stuff that we didn't actually need. Like there was a whole heap of services in the OS that we didn't need. So we're deploying that, then we're either taking stuff out, or then we're running security over it for a whole heap of stuff that we don't need at all. So we were like, we need to get rid of that. And the operational overhead of that is huge, like I spoke about. Like, how many people or in a past life looked after the operationalization of patching a fleet of servers? How many people enjoy doing that? Oh, we have one. Oh, well, that's the first time I've got someone say yes, well done, sir. If you must like pains, that's each their own. It's good. It's all good. And as I spoke about, the security attack vector is massive, right? So there was a really good talk at the KubeCon keynotes this year in Copenhagen that showed how many lines of code there are before your code. And it's something like in an OS all the way up, even including Kubernetes, there's over like 10 million lines of code, right? And then you've got your code, which is about not even 1%. So think about all the stuff that's in there that you just take for granted before you even get to like your code. So there's a whole heap of stuff that can go wrong there. So we wanted to have the OS as lean as possible, as light as possible. And then Even traditional OSs are slow in the cloud to boot. Like you're talking a couple of minutes. We wanted to get that right down if we could. All right, I'll let you.
So essentially, we wanted to build an OS that works in any cloud provider as well as on-prem. A lot of our customers over in the US and around the world still have, a large footprint in technologies like VMware and stuff like that. So we want to include those as well as people looking at cloud-native stuff. We wanted to be able to build the OS in CD using the GitOps sort of workflow that Gabe mentioned earlier. We wanted to be able to apply any security controls that we wanted to easily.
There's an asterisk, so we'll get back to those security controls. There's a whole talk on these security controls, but I'm actually going to reference a blog post that's really...
And as Scott mentioned, traditional OSs are slow to boot, so we wanted to be able to boot that OS quickly by making it as lean as possible.
And I actually forgot one of the things that we wanted, or we only wanted to run containers. That's all the OS needed to do. We wanted everything to be containerized. So every service is a container, everything's a container. There's a massive security plus to doing that, because once you've got control of the kernel, you can start using C groups, AppArmor, or a whole heap of stuff to protect it. You can actually start protecting your Unix socket and then looking at what can talk between it. It's actually super, super cool what you can do on the security side. So I could do a whole talk on that, which is not this talk. There is a really, really good blog post that went out like a couple of days ago from Jess Vassell that talks about how there is already security controls in place in the container world. So imagine if you could take those same controls and put it on the OS, because the OS kernel is only running in a container. It becomes super, super powerful. As I said, I could do a whole talk on that. I actually did do a whole talk on that last Container Camp, so check it out if you want to see it. But check out this blog post. Awesome stuff. Awesome, awesome stuff. Okay, so we know what we want to do, right? Seems pretty straightforward. We're just going to build the OS. We had two options. This is what we looked at when we started. We looked at CoreOS and we looked at LinuxKit. We really did like CoreOS. We heard rumors about the acquisition, and we got cold feet. So we went back to LinuxKit, because it predominantly was started by Docker, but it's open source now and it's in its own LinuxKit namespace. There's a whole heap of people contributing to LinuxKit now. So you've got people from Arc, you've got people, ARM, IBM, us at Puppet. There's a whole heap of people. I believe it can run, someone's trying to put it on like the IBM mainframe system as well. There's some crazy stuff going on in the project. So what did CoreOS lack? We didn't have control over what we wanted, so the GitOps workflow, although you could have had the configuration in CD or in Git, sorry, we still would have had to have an OS that's somewhat modeled on CoreOS. There's already an OS there. We were tied to Docker, and I'll give that a quote because we'll come back to that. We couldn't apply the security controls easily that we want. So the security controls we spoke about in the blog post and stuff aren't really accessible in CoreOS, and they were in LinuxKit. So the winner is LinuxKit. What is LinuxKit? So if you don't know, I'm just going to go a quick run through. It's a lean OS. It's defined in the YAML. The 4.14 kernel is standard at the moment. Allows you to run any container runtimes. So that was super important. One of the things that coming out of KubeCon and that was like, hey, we had customers, well, I've had a customer ask me already, can you run gvisor? I was like, yep, we can do that. We just need to configure the runtime and stuff. So the fact that this allows us to run any container runtime, because we can bolt into what we need. As we go further down the talk as well, I'll start talking about Cry. But this gave us the basis to be able to start looking at all that stuff and not be locked into anything. LinuxKit comes with a whole heap of services that you can use straight out of the box that ship with. So it's in Docker Hub, LinuxKit / whatever you need. You can use those services yourself, or you can build your own, and you can bolt them into the OS. It's really good. And all system services are containers. So that's what we want. You can talk about this one if you want.
So I guess the difference between Linux Kit and a traditional OS is, as Scott's mentioned here, there's a smaller attack surface, so all of the stuff that we mentioned earlier, about the bloat that comes with the traditional OS is essentially all you're putting into that operating system that you're building is the stuff that you need. It's entirely immutable. System services are sandboxed.
So yeah, that comes back to, again, we can use control groups around system services, so you can see what they can speak to, what they can load, and a whole heap of stuff around that, which is, again, from a security point of view, super cool.
There's specialized patches and configurations. You have full control over the build in your, whatever CI/CD system you're using, and the configuration is all YAML, for those of you who like YAML.
Yeah, so I've got the wrong heading on this. But yeah, this is Linux Kit, so it's just a YAML file that's in CD. And then you can like Gabe said, talk about when do you want changes and things like that. You can put in a pull request to say you need something being added to the OS. You can have the conversation around that on GitHub. And then you can also have the conversation about why you need that in the OS or why it shouldn't. It also allows you to do compliance tree checks around things like when there's something like a CVE and comes out, you can say, like, well, on this date the CVE come out, here's the new version of the container with the patch CVE, here's the pull request to put that in, and you've got a really neat timeline of how you dealt with that CVE. So we'll have a quick look at the moment at Linux Kit. So I'm going to do two things at once here. I'm going to just build it. So this is just going to build a Docker one. So this is YAML's just local. On the other hand here, I'm going to show you how it builds. It builds in just a couple of minutes. I'm going to show you like what we can do. So we've got like Docker installed. I'm using containerd at the moment to talk to the. I'll give you some background on what I'm doing. So I've got all my services in namespace, so I've got control groups across them. I'm actually using containerd to talk inside the Docker container. So as you can see there, I'm running Docker. It's not the latest version. But yeah, I've got the OS there. I'm using containerd to interface in through a control group into the Docker container. The Docker container actually is a full working version of Docker. It's not just some sort of shim of Docker. So it's kind of like Inception. It's containerd running Docker in the container with another version of containerd and run C. So I've actually got two containerd to run C. What that means, but though, is I've got process isolation. And from security, that's really cool. And then I can just go Docker run. Where it is. Oh, terminal size. And then you can see there that I'm running Redis, and you can see that I can accept connections. So that's fully operational. I've got an OS that I've just built. As you can see, it's just building on the side there. And on the other side, so I've got to, pump my terminal size up. No. Oh. It's not happening for me. Yeah, it's not letting me do it. Okay, sorry. So what's happened in the two terminals on the side? So you can see we had the OS. On the other side, while I was talking and got in Redis running, the OS is built. So that's how quick it took to build an OS from scratch. So in tandem there, what we've done is shown you that, hey, we've got the OS running Docker with containerd as the interface, and we've run Redis. So in the instance of what we were doing, why I use Redis is it's like super small and it's Alpine. If I used Kubernetes, it would have been a little bit slower. But this is just showing you like what we can do. So as you can see there, it's a fully operational version of Docker inside Linux Kit. It's running, and on the other side of the terminal, we built it in that time when we ran it. So as you can see there, we've already achieved efficiency. Some of the security controls we wanted, and it's operational, right? So imagine now that that was Kubernetes instead of Redis, we would be pretty much done, right? So cool, we're done. That's it. Talk soon. No. What about day two concerns of running the cluster? What we have now is a single Kubernetes node. It runs on top of Docker. So yeah, as I said, imagine that was Kubernetes for the sake of. We will get to Kubernetes later. It just takes a little bit longer. It runs an OS, and it's about 1 gig in size. And I thought that was really cool until I spoke to Angus last night, and he was like, "That's terrible. I did it for like 40 megs." And I was like, I don't want to even turn up in the morning now. Thanks, Angus, if you're there. Yeah, it was good. I thought it was good. So one of the things about the size is we need to ship it to multiple clouds. So this works on Azure, this works on GCE, this works on OpenStack, AWS, and VMware. So when you're talking about distributing this all over the place, like the size matters because download size equals speed. And it runs on top of Docker, like we said. So we can, like I said, we can go home, mind's blown, everything's good, talk's over. Yeah, it's not usable though. What we have there is a single node of Kubernetes, which is good. But a lot of, I haven't seen many people run a single node cluster. The problems that we just created for ourselves. We can't easily join another node to the cluster. So we've got an isolated VM running Kubernetes, which is awesome. That's what we set out to do. And we were so focused on that, we actually forgot about the authorization of that. But that's okay. We're not, it wasn't due to be released yet. How do we do updates? Like, so we've got ways that the infrastructure is immutable, but how do we actually do any updates to it?
And then obviously, one of the most important things is how can we make customers' data persistent, because despite the fact that everyone wants to run the magical 12-factor app that Gabe talked about, at some point we have to store state somewhere. Yeah,
so a perfect example of that is customers' data persistent. That might not actually be state of their application. What about their etcd cluster? So when you're doing updates of Kubernetes, and we need to keep cluster state, so we're removing the nodes and things like that. How do we keep backups of the cluster state? So when we bring in a new node, etcd still has consensus and things like that, which is not an easy problem to solve. So we did achieve all the goals we wanted at the front end, kind of. And we're now, like every software project, we've discovered we created ourselves a whole new set of problems that we need to solve. So how are we going to go about that? Problem one. How do we orchestrate the orchestrator? This is quite a problem for us now. So we're running Docker. So how do we do this? What we need something to interface into the kubelet container to do cluster state and also be able to run tasks against the cluster to see how it's polling. By that, it means we need bidirectional streams between nodes, because like there can be events on a node that gets triggered from the node that needs to be sent to the controller and vice versa as the cluster's spinning up. And we need to access an external interface to cluster configuration. At this point, all the certificates and stuff are generated from the new cluster, but beyond that, we can't configure anything else. So imagine a customer's not just going to want stock standard Kubernetes where they can't configure anything or do anything. And like things like we don't have how many etcd nodes, how many controller nodes, how many worker nodes, a whole heap of stuff that customers will want to pass in a blob. We don't have any of that at the moment. So as we said, this is the major problem we need to solve. I'll let you talk about this a little bit.
So I guess the options that we looked at were using Docker Swarm to bootstrap Kubernetes. Alternatively, changing the runtime to a lower level application to give us more flexibility, or writing our own service to bootstrap the cluster.
Now, it might sound crazy that using Swarm to bootstrap K8, but that's actually what Docker Enterprise does. So if you have a look at the new Docker Enterprise product, it actually uses Swarm as the bootstrap mechanism for Kubernetes. It's a good solution. It works. But for us, when we were talking about like trying to be lean, it kind of looked like we were building a car and then putting another car on top of it, and then sitting in the top car and looking at the bottom, hoping that car was going to drive straight when there was no one driving it. So it was kind of a weird analogy. That's a weird analogy, but it was kind of like weird that we would have a cluster orchestrator with its own Raft protocol, and then have another one on top of it with its own Raft protocol and a few other things. So it got messy really quickly with that, and we were like, no, we don't want to do that. I mean, with Docker themselves, they've taken out the Raft protocol and done a few other things that we just didn't have time to do. So what we looked at, we changed the runtime. So we removed Docker completely. That gave us flexibility to have gRPC interfaces into the container runtime through containerd, which is something close and dear to my heart. And then we decided to write our own service as well, called Bootstrap. We had no other better name for it, and a Bootstrap for cluster, so it's got the name Bootstrap. That was my creative genius right there. Luckily, I'm better at writing code than I am naming stuff. So we'll just go through a bit of what Containerd is for people that are not familiar with it. How many people are familiar with Containerd here? A few? Cool. It's now part of CNCF. It was originally part of the Docker engine. It is part of the Docker engine still, but it's been broken out and it's owned by CNCF. There's contributors on it from Google, us, a whole heap of people. And what it basically does is it gives you like some stuff that the Docker engine does, but most of it's like much more low level. So it gave us the building blocks that we needed. And it also allowed us to have different runtimes. So like if someone wanted to use gvisor, we could actually have an image now or an OS that has gvisor in it for Kubernetes. Not that it's like stable at the moment, but for testing purposes and things like that. But it gave us the flexibility to future-proof because we could easily change the underlying runtime from runc in Containerd because that's all supported now. We have been playing around with Kata containers, but I don't think it'll work in this OS because of different levels of virtualization and things like that. But the main important thing is Containerd has got a gRPC interface and a local Unix socket, and that's what we wanted. And there's protobuf specs between all the components inside Containerd, so it's super easy to work with. And just a big shout out to some people that helped us with this project on Containerd, like Stephen Day, Phil Etz, on the Linux Kit side, Justin McCormack. Big shout out to all those guys because they helped us out with all this stuff. So this is the architecture of Containerd. We actually were only really cared about the gRPC interface, tasks and events. We get a Prometheus exporter out of the box, which is always good, so we can get metrics out of that. We cared about the runtime swappability. So everything we needed was there. All the stuff that was inside Docker, there was a whole heap of stuff we didn't need. And like Swarm and stuff, if we weren't going to use it, we didn't need it to be there. And yeah, Containerd made a whole heap of sense. So that's the CLI that you get. It's not the same. It doesn't contextually work the same as the Docker CLI. So like an exec isn't a Docker exec. So in Containerd world, the container is actually just a file system with no process running in it. The exec is actually the process that runs inside and spins up the container. So you have to give it like a process ID and things like that. You have to be able to track it. It doesn't work exactly the same as Docker exec. It allows you to manipulate namespaces, which is good. It allows us to have control over security, which is good. And there's a whole heap of stuff that's a low-level primitive for building an OS. And I'll let you talk a bit through this.
Okay. So what Containerd gives us is OCI image spec support. So essentially that's portability across a whole bunch of different sort of container-related runtimes and stuff like that. Runtime spec support for like runc. Image push and pull support, so the same sort of functionalities you would expect with Docker. Network primitives for creation, modification, and deletion of interfaces. And
just a quote on that, that is not on, like, that's in the network namespace it's already created on the container side, not on like the kernel level side. So in the Kubernetes, actually CNI does that, but so the query interface can talk to CNI, but this is more on the container level. So just a text in case someone goes, actually you can't do networking with Containerd. You're completely right if you said that. This is the network manipulation inside the container.
And finally, management of network namespace. There's containers to join existing namespaces.
Okay, so that's the get out of jail free card at the bottom there. This is how it works with other projects. So Moby, Cry, Containerd, which is actually a Go plugin now inside Containerd. It's not its own project. It is its own project, but it's inside the Containerd binary now. Runtime. So as I said, runtime can be gvisor, it can be Kata containers. And you can run C's like the default, and then you've got all the other stuff that you need. And this is how it interacts with Kubernetes. So you have Kubelet, which obviously has Cry. It speaks to the Cry plugin, which is now a Go plugin inside Containerd, and then you've got containers there. So that's the workflow of what we got by changing to Containerd. And as you can see from what we were trying to achieve, this like simplified everything for us and gave us everything we needed. So we'll just do a quick demo now. So we're going to do the same thing with Redis. So you can see here, one of the things that, I'll just pull it. CTR, you notice here that I've said like it's docker.io.library.redis. Containerd is not opinionated about which container registry you're using. So you could be using Quay or Google or anything else. So you have to be fully qualitative, where Docker already assumes that it's Docker Hub. So our case just so it'll be a little bit quicker. But as you can see here, we can pull. It works nearly exactly the same as it does in the Docker world. That's already there because I cached it. And then again, we can go CTR run. I have to do nethost because it needs network functionality to boot up. If not, it wouldn't work. And as you can see there, we're running Redis. So we basically, inside Linux Kit now, have got the same image that we had before. We've ripped Docker out. We're running Containerd actually at a lower level inside the main OS services. So now we've just got run C, Containerd, and then we're running containers on top of that now. So we've made it even smaller. We've made it less moving parts, and we've made it more simple for ourselves. And we've got a gRPC interface now for Kubernetes, which is what we want. We removed it. So what we've done by essentially that is we expose the gRPC interface so we can start talking inside through Containerd, which is actually the same interface that the CTR CLI is talking to. So now we've got to build our own service. We decided to do it. And if anyone knows what movie this is from, you get 10 points. Yeah, someone said it. All games, all done. So we had this idea of Cream, which is Kubernetes rules everything around me. We built. So any Wu-Tang fans out there? No? Yes? There we go. Yes, it's always good when you get someone throw up the Wu-Tang sign to you at a talk, 10 conference. So we built this thing called Cream for the Puppet module. And basically what that was is it's just a really naive shim over Vagrant that builds nodes in asynchronous format. So the Kubernetes cluster comes up, Puppet module does it, builds it without the Puppet master does Puppet apply, and it builds it all in about 5 minutes. The reason we actually built that was because we are a distributed team. We're in Sydney, Belfast, Romania now. So we're all over the world. Not everyone is as knowledgeable at Kubernetes as like myself and Dave are. So we had to make something simple so other developers were able to start working like on a follow the sun method. And this is how Cream was born. And Cream was just something that I was doing, so it was quick for me. And then I'm like, Dave, check this out. And he's like, that's awesome. And it started, and it's almost just become its own thing. So this is Cream v2. We've got rid of the Puppet. We've got rid of the Ruby. Thank you. Ruby's gone. The Cream client's actually go now. What the Cream client actually does is it interacts now on the CLI and mimics the upstream service that's going to pass the configuration into the Linux Kit image. What that does now is it emulates what the upstream, like I said, the upstream Puppet for pipelines configuration blob is. So it's going to actually pass this information blob over gRPC of the configuration that it expects Kubernetes to be in. Now we can start to do configuration of the Kubernetes cluster into more what users want. We've built Bootstrap. Bootstrap is an application that we built internally in-house that runs in a container on top of Linux Kit. What it does is it talks to Containerd through gRPC. And over in Unix it talks to kubelet and starts configuring the Kubernetes cluster. And what that allows us to do is to check things like etcd consensus is up before the nodes are up, other nodes are up, make sure that all the certificates are there, all the Kubernetes services are starting. So this is working at the moment, and yeah, this is we're getting close to where we want to be, right? So this is awesome. So I'll show you a demo of this one. Here's one we prepared earlier. Oh. So this is just another Linux Kit image, and I can just do Kubernetes get nodes. Hey, there it is. We've got a Kubernetes master, and as you can see, there it is, etcd, it's running Weave, it's got everything we need, and the OS is now it's around about 800 megs. And it's actually got a persistent disk that's separated from the immutable part where the Kubernetes is running. So the etcd data is actually mounted into a disk that can be persistent. And now what we can do is we can do upgrades by changing the Kubernetes version of the OS and keep the persistent disk and do in-place upgrades. So that's super awesome. At the moment, there's one node, so it's obviously downtime because it's hard to do in-place upgrades on one node. But we're starting to look now how we can replace the Kubernetes version and change things out. Now when you start to think about this in the cloud native world, this would be a disk in Azure or a disk in AWS that is an EBS volume or something, and the customer data is there. We replace the OS image and we remount that volume, and then there's your upgrades. And that's how we start to patch the OS. That's how we start to do operational changes and things like that. So now we need a second node. So what happens is the Bootstrap talks to another Bootstrap instance inside, and then it talks to its kubelet. That's bidirectional gRPC. What we're actually doing with security, so the first thing we thought of with security is like, what if there's a man-in-the-middle attack and someone says, hey, I'm a node as well, and I want to jump into your cluster when it's configuring. What we actually do, we expect inside the blob that comes in from the Cream client or the upstream provider is actually a list of IP addresses or host names of the cluster. If any requests come in on gRPC that's not from that list, that's on the whitelist, it actually doesn't accept the connection. The reason for that is at this time, this is the most dangerous time for vulnerabilities because we're passing admin credentials to Kubernetes across multiple clusters via gRPC. It is gRPC SSL, but there is some risk involved here, so we're trying to mitigate as much as we can because, yeah, if it's cloud native and it's in a cloud, there could be a rogue instance. Could be we're considering that there could be a hostile instance at the time when the cluster gets built. So yeah, once Bootstrap's done and it knows now the instance list of what should be there in the Kubernetes cluster, once it's seen its job's done, it actually rips itself down. It says, hey, the cluster's good, I'm all good, and then it's got a kill signal that sends to it once it's all up. The reason we've done that is so the gRPC service is not available once the cluster's up, because again, that service once had admin access to admin credentials for the cluster, and you just don't want an open service there. And we spoke about security earlier on. Because at that point, once the cluster's configured, we then pass the credentials for Kubernetes up to the upstream provider, and then the next, whatever's the master of that will run it. How do we talk about updates? Unfortunately, we can't talk about it, but we've got this funny GIF, because this is another project we're working on that I can't talk about yet that's in R&D, but I can give you an architecture document and call it Mysterious Project X. So let's tie this together for what this means for a customer. So we have Mysterious Project X that talks to your cloud of choice. It understands how to provision the image, which is a Linux image. It also understands how to provision the volume store, whether it be on Google or Azure. And then gRPC, Bootstrap works. It talks back up and passes to the pipelines for containers, and then that admins the Kubernetes cluster once it's running. And Bob's your uncle, you go to work in Kubernetes cluster in immutable, I'm going to say somewhat secure OS. I mean, everything can be hacked, but we've thought about it as much as possible. And as I said about upgrades, you can just remove, keep the EBS volume or the volume there, replace the image with the new version of the Kubernetes, and then the cluster comes up and it all starts working. We're working on rolling updates and things like that at the moment for multi-controller tiers. If you're on Slack, Puppet, Docker, Kubernetes, Scott EC, just hit me up. I'll answer any questions.
Perfect.
And thank you.
Hanging out as well, so perfect.
Thank you.